we stand on the verge of a revolution in computing technologies, a quantum computing revolution. At an abstract level, what a modern computer does when it's performing a calculation is almost indistinguishable from what a person does when they're working with a pen and paper. It reads in some small amount of data, performs a simple manipulation of that data, and then writes it to storage. It repeats this process over and over again until it reaches an answer. The main difference between a modern computer and a person is that it can perform this cycle billions of times a second. Imagine, however, if computers weren't limited by this analogy to human behavior. Imagine instead if they were limited only by the laws of physics. In this case, we'd have a new type of device, a quantum computer, which instead of reading and writing data that was analogous to our scribblings on a piece of paper, it instead wrote and read and manipulated the basic quantum states of matter. Such a quantum computer would be capable of implementing far more efficient algorithms than are currently possible with conventional computing technology. It would also open the doorway to new forms of cryptography and unconditionally secure communication. My work is at the intersection of these two fields, computation and cryptography. And one of our most interesting discoveries, in my view, is the discovery of protocols for blind quantum computation. Blind quantum computation allows a user to encode a computation in such a way that it can be delegated to a remote server with complete privacy. So the server running the program cannot learn anything about the program itself except for bounds on the resources used, the time and space required to execute the program. We subsequently realized that our protocols could be modified to enable detection of errors introduced by a malicious server, so that the user is able to detect any tampering of the program, so that the outcome can be verified. We were able to work with colleagues to demonstrate this in experiments in Vienna, which use photonic systems to implement these cryptographic protocols. So while these are only technological demonstrations, they do kind of illustrate the path forward. So what's the future for secure communication, secure delegated computation protocols? Well, initially, any practical protocol is going to be small scale. It's going to involve simple devices over short distances, such as between racks in a data center or between neighboring buildings. Over time, however, we can expect the emergence of metropolitan area networks, national networks, and eventually a quantum internet. And that's something I'm really looking forward to. I'm Joe Fitzsimons from Singapore University of Technology and Design and the Center for Quantum Technologies. Thank you.